Hello and welcome back to the lab. The previous video, I have a longer lag time than I was expecting, and I wanted to get something out on YouTube, so this is the next thing that was waiting in line. Today on the bench we have a 067-0502-01 calibration fixture. This is actually the older version of the PG506. So the PG506 the calibration generator gives the stepped voltages. This one actually goes a little bit lower than the PG506 from 0.2 millivolts all the way up to 100 volts. This one does the same thing in calibrated steps. The PG506 also adds the 106 functionality to this. So a 106 and a 0670502 equal a PG506 without the percentage readout. That's the only thing you don't get. So this was the last piece that I needed to complete the set of the type style of calibration gear for scopes. So I'm glad I could add that one to the lab. I'd like to get a frame for it. I think this is a factory frame. I don't think this is a... I think it was shipped with this case, but I'd like to get it in the other style of case if it did ever go in there. I don't know. It's got the locking bolt and it's got the grooves cut out for it, so I don't know. I haven't plugged this in. I haven't turned it on. I haven't even cleaned it yet. So you guys see it exactly as it came out of the box. Hopefully this isn't too banged up. The box was in pretty rough shape when I got it, so it was wasn't looking the best. But let me plug this into my isolated supply. And the isolated supply is running about 118 volts. I've got about an amp of current limit switched in. So haven't even taken the case apart yet, so let's see if we get at least a pilot light. I have a little bit of glow on the bulbs that just went out. So something charged up and then came down. We're drawing about 20 watts of power. Pilot light on? Oh yeah, it is on. It's just really dim. So we do have a pilot light. Let's see. I have some tubes lighting up. Tubes have come into emission, so we're drawing more current. We do have a bit of voltage sag, though. 19. Let me give it some more current. That brought the voltage up. Okay. So, looks like we're okay. I don't see anything drawing excessive current, and we have no shorts. Let's see if it's actually doing anything. There's some damage on the BNC. I'll set it to 50 volts. Oh, hey. We have a square wave. We're a bit high on the calibration, I think. I have an adjustable square wave. That one actually looks pretty good. A little high. So we're a little high on the calibration. Alright, well, let's take a look at the inside of the unit and see what it looks like. Okay, so I've got all the screws out of the panel. There's 3 screws on each side. The top panel just lifts off. So let's take a look inside and see what we're dealing with. Oh my. All right. That needs a bath. Nothing too crazy. Just it's gotten a little furry. Interesting mix. There's a tube here, tube here. These are cans. But then we have some solid state devices in there. So that's interesting. So this is like the other devices in that series. This is a mix of solid state and tube equipment. Okay, this one does have the adapter board. So this is a Compactron tube. So they had so this is actually one of the, not the original units, it's the later unit. They swapped it out with this adapter board right here, and then this is a Compactron tube. Alright, so we have transformer, rectifier, bulk filters, regulation. This is Precision City right here. Take a look at this. There's the magic in this unit right here. These resistors. So I haven't looked at a schematic yet, but sorry about bumping the camera. I'd be willing to bet this is just a resistive divider to get the output voltages. So there's an oscillator to make the square wave, and then the resistive divider just sets up the amplitude, which means that I'll have to look at the calibration document. Calibrating this could be pretty interesting because its input impedance is probably going to play into that resistive divider. So if scopes have a 1 megohm input impedance, so if this uses a meter, meters have 10 megohm input impedance, it'll throw off the resistive divider a little bit. So that may play into actually having to calibrate this thing. Although with that being a resistive divider and not many adjustments, I'm not sure exactly what the calibration is. It's just going to be, are the resistors in the spec or not? Okay, there's our pilot light. What's the bottom of this thing look like? Let's see, we have ceramic strip construction, which that's par for the time. There's a couple, these might be resistors, these might be little couplets. Not sure yet, I'll have to look at the schematic. Couple of capacitors that I want to change out. These silver mica ones are going to be okay. I don't want to mess with those. But we'll check these electrolytics and see what's going on there. I'll definitely want to get these bulk filters out. Those will go. I got a bulk filter right here, I got a bulk filter right there. I'll probably do my normal trick with the adapter boards and get those slotted in. Also, doesn't look like the BNC jacks are going to be too terrible to change out. I may source a BNC jack for this thing. Given the damage on the front of this one, we'll see how it goes. Those are some bigger old style diodes. Another electrode down here. That might be the reference diode right there. That gold package. Let me zoom in on that. This guy right here may be the reference. The other thing that's cool about this is you can hook this unit up to an external reference. So if you have a more stable reference in the lab, you can look it up. I have to see what the parameters are for the reference for this, but no, the construction looks really, really good. Everything looks great. I'm going to overrate these caps because this is a tube unit. So the reason you want to overrate the caps a little bit in a tube unit, voltage-wise, is as the voltage or the tubes take a minute to come into emission. So because they have to warm up. So when you switch it on, this has silicon and tubes in it. So the silicon's there. It just slams in, full voltage, everything's there. The tubes take a minute to warm up to start drawing current to pull the rail back down. So you get this voltage come up, and then it comes back down. The cap has to be rated to take the highest amount of voltage it's ever going to see So at that startup, it can actually blow these caps before the tubes just warm up, because the tubes take about 30 seconds. So on the older caps, they were much more tolerant of overvoltage, short-term overvoltage, than newer units, than newer capacitors. Newer capacitors are not tolerant of overvoltage at all. So that gets into a little bit of the chemistry of the capacitor and the way the dielectrics are forming and things like that. So if anybody's interested in that, I can go into that a little bit. Old, you can spike it and then have it come down. New, you can't. So they pop and blow their top. This guy will be fine. He's a poly. And then I have some silver mica or some mica caps, some ceramic disc. I don't see any other resistors. Don't look like they've been heat stressed or anything like that. Everything actually looks pretty good. We'll probably check the values of some of these resistors just to make sure they're sane. Get some caps put in, and this guy will probably be good for another 40 years. Actually, he's probably about 60 years old now. I think I'll have to look, but I think this device is a 1960s era, which would put him at about 60 years old. So, yeah, so I'm going to get started cleaning. I'll give this thing a bath. My hope is that I do not have to mess with those precision resistors. I will definitely service that wafer switch, but if I don't have to mess with those resistors, that would be ideal. That would be a problem for this unit if I had to get in there and play with those, but hopefully not. I'll also check the health of this tube. Precision resistors from the late 60s. That still amazes me a little bit. Those are just wire wound. A lot of handwork went into those. Gold leads. We'll be careful, and we will take care of those gently. Okay, I've done a short bit of cleaning and done a first pass of cleaning, got everything dusted, serviced the switches and everything like that, got everything done. And I was looking at this Compactron tube, and I was noticing that some of the tube got really hot. Like there's some heat damage on the metal and things like that. So I'm like, oh crap, do I need another tube? Is this one getting close? So I'm gonna zoom in here, and you can see on this side of the tube over here where it's got some discoloration and things like that. It looks really, really warm. This side of the tube looks okay. And I was like, oh crap, do I have a weak tube or what's going on? Because these are kind of hard to test, and I don't have a tube tester yet. That's one thing that's on my list of stuff to get. But I'm going to turn the unit on and have you take a look and see what I found. So unit is now on. Look how bright the cathode is on the power side of the tube. That's just cathode heat, I think. I don't think the tube's actually having trouble. Here's the cathode on the on one of the elements of the tube. But look at how bright that cathode is. So that is why we have some heat discoloration on that side of the tube. It's just normal operation, I think. So I think we're okay there. The other tube looks good and everything. I'm going to shut it off. While I was doing the inspection, I did find... Oh, and tube number is... This is a 6GH. It is not a 7734. It is a 6GH. Which is what's supposed to be in here. So that's fine. But on the flip side of the unit, so just doing a visual inspection, we have a little bit of crust around this capacitor right here. This capacitor is actually leaking some electrolyte. That's part of this green death here. So that settles it. Even if they do test good, these guys have been in there so long, they are up for a timely replacement. We will be servicing the capacitor section, or the capacitor points on this board next. Okay, while I wait for some critical components came in, So while I wait for some power supplies to warm up, I figured I'd get started in some of this. So I have to adjust the power supplies in this order. The 300 volt supply, the 125 volt supply, and then the 100 volt supply. Now all these supplies are floating because of the transformer, and they're commoned to each other. So because they're floating, I can't hook the negative lead to the chassis and do the proper measurements. So I have to figure it out. Also on this one, the service manuals are pretty sparse compared to some of the other scopes and things that I've been working on. So there's not a lot of information to go on. And there are no test points. So it says adjust the supplies, and there are no test points. So have to come up with our own test points. To find the common, I'm picking it up on R422. There's a 100K 5%, which happens to be this guy on top. And I want to pick up the common on the far side of the resistor from the pot. So the pot hooks up to the resistor on this side. We're hooked up to the common on the other one. That's going to be common for all my measurements. So that's where I have the common lead hooked up, and that will be common for all the floating supplies. First test point for the 300 volt supply is on the far side of the potentiometer again on R420, which is a 330K, which happens to be the third resistor on the bottom. So if you look, you can actually see the lines where the pot hooks up on this side. So we're on the far side away from the potentiometer, so that's what we're referencing. So for the 300 volt supply, this is my test point. These are my test points. I'm going to get this resituated so I can do the 300 volt supply. Okay, so the 300 volt supply needs to be within 2%, which is an allowance of 6 volts. We're at 300.2, so we are fine on the 300 volt supply. Okay, while I wait for the meters to stabilize again, or the unit to warm up again, because I had it turned off when I moved the probe, I'm probing right here at this point. Here's the potentiometer. I'm probing on the far side of this resistor to get my 125 volt supply. I did not need to move the common because the 125, the 100, and the common are all on the same circuit. So I need to just wait for it to warm up and then adjust this for 125 volts. And if I go back to my calibration document, that needs to be within 10%, which means I get 12 volts out? Yeah, I got a 12.5 volt allowance. After the adjustment to the 125 volt rail, we have 125 volt 0.0 on a 10% allowance. Good enough for me. Next up is the 100 volt supply. So let me move the probes and I'll show you where I'm picking that up. Okay, I checked all the parts around the negative 100 volt supply and I couldn't pick up the 100 volts safely with the probe. So what I'm going to do is I'm going to I know from further on in the calibration this is the reference supply and we have to adjust this for 100 volts. So I'm just going to check it at the barrel jack because I have the knob set to 100 volts and I have the mode set to DC, which is actually the next step after we adjust the supplies. So I'm getting 99.959 into the meter impedance. So that is good for the calibration. It's in the realm of adjustment. I now need to check the negative 100 volt DC supply, which is ground referenced, if I remember correctly. Yes. And the 100 volt supply should be between 93 and 107. So we'll check those two here in a second. I need to get another schematic to find out where those test points are. And then I will be back. Okay, so that's why I was having trouble finding the supply. This is my 100 volt supply adjustment resistor. I was sniffing around this resistor for the supply, so couldn't find anything. That's the negative 100 volt supply, which we need to adjust right now. Okay, here's the test setup for the negative 100 volt supply. We have on this big resistor right here, left side, that's our negative 100 volt supply. Ground is up here on the chassis. And here's our negative supply, 100, slightly over 100 volts, 33 millivolts on 100 volts. So good to go there. At this step in the procedure, I need to put the unit back in its case, let it get good and warm, get it up to operating temperature, because we have to adjust the 100 volt, do the final adjustment on the 100 volt supply into a 1 mega ohm load. Okay, on the right-hand side of the unit, when the case is closed, there's a tiny hole right here that you can get a tuning tool in, and you can adjust the reference voltage. So when the case is all closed up, everything's nice and warm and toasty and at a operating level, you can tweak the reference and not have to go back in. This is a 1 mega ohm, 1% resistor. There's the part numbers and everything. These weren't cheap, but got 5 of them. Ran them through a 2-wire resistance measurement on the 7510. This one ended up testing the best. It was 1.0009 mega ohms. So I got 3 zeros out of it out of my 5. That was definitely the best. They're all within spec for doing this. The spec is a 1% resistor. These are all 1% resistors. This one out of the lot just happened to be the best 1% resistor. Here's the 7510. We're going to crank this all the way up to 100 volts. That is not bad at all. Let's see what we can do to get that a little bit better. I'd say that's about as good as we're going to get it. Let me back this range down 1. I can see some movement on there. I'm barely touching this control to get it to... I am not going to mess with it from there. That's about as good as we're going to get. So you're actually seeing the noise of the reference in the cowl fixture at this point. I want to tweak it up because I want it to, if I want anything, I want it to be a touch high. This is a multi-term pot. This was a exotic part for the time. Can we squeeze a 3 out of it? I think that's going to be good once it settles. It's going to settle just above 100. There we go. So I am good with that. That is perfect. So let me spin this down. Actually, I need to check them all now. So we can just check the accuracy of the load resistors. Here's 50 volts. And that's within spec. I'm allowed 49.95. 20 volts. That is within spec. 10. Yep, that's within spec. 5. Ooh, perfect. I'll take 5. 2. Perfect. 1. Perfect. 0.5. That's within spec. 0.2. That is within spec. Let me drop my range by a lot. That is well within spec. 0.1. well within spec. That's 50 millivolts. The service manual actually doesn't even specify anything other than 0.1, so I'm just going to run these down to make sure we don't have anything too crazy. Looks good. That looks good. That looks good. That looks good. That looks good. This is 2 millivolts. 1 millivolt. That looks good. Let me drop the range on the meter. No, that's the lowest range my meter goes. So this is going to be 500 microvolts. Exactly. 200 microvolts. I'm good with it. So that's actually fantastic for a unit that's this old, being referenced on a brand new in-cal, in-spec 7.5 digit meter. So well done. Gonna switch over negative. Yep, let's run it back up. 500 microvolts. Yep. 1 millivolt. Yep. 2 millivolts. 5 millivolts. 10 millivolts. 20 millivolts. 50 millivolts. Pop this on auto. 100 millivolts. 200 millivolts. 500 millivolts. Volt. 2, 5, 10, 20, 50, and 100. DC minus is working too. So that is perfect. Let me kick this over to square wave. Let's see if our square wave looks good going into a scope. Okay, I have the scope set up. We're at 20 millivolts and we're at 5 millivolts per division. So we have 4, 10, 50, the noise you're seeing in the trace is actually the readout. I have the readout turned on, so you're just seeing time, beam time. 100 millivolts, perfect. 50, 200 millivolts, looks good. Volt, that's 500 millivolts at 100 millivolts, perfect. 200 millivolts, 1 volt. Perfect. So a little bit off actually on this plug-in. So this would be error in the plug-in because we know the calibration fixture is correct because of what it was putting out to the meter. So this is actually going to be a plug-in problem, not a calibrator problem. That's 5 volts. 10 volts. 20 volts. 50 volts. And that's as far as that goes. So, yeah, square wave generator looks good. Everything looks on point. I don't actually have anything to test the current side of things, so I'm going to leave that go for now. But this guy's ready to work on some scopes. Thanks for stopping by and taking a look at this calibration fixture. I got a lot of questions on that how to calibrate a scope video on a couple of the different plugins, the 106, the PG506, and the TG501. If you guys would like me to do another video like that and go into some deeper detail on how those instruments all work together to do a scope calibration, let me know. I do have some full scope calibrations coming. I'd like to get a couple of the 400 series and a couple of the and some more 7000 series stuff on the channel, so let me know if that's of interest. The main difference is a PG501. So the short answer is a PG501 combines this unit and a Type 106. So if you have this and a 106, you have the older style PG506. So the PG506 gives you the calibrated square wave steps. Doesn't give you the DC and the comparisons, but it does give you the calibrated amplitudes for the scope cals. And it also gives you the sweepable high amplitude square wave, and it gives you the 1 nanosecond fast rise and fall outputs. The main difference between the 106 and the 506 is drive current for the tunnel diode pulsar. The drive current in the 106 is higher than the 506. So the 506 can and sometimes will drive the tunnel diode pulsars. They're not guaranteed. The Type 106 is guaranteed to drive the tunnel diode pulsars because it has the drive current available. Both of them will output high amplitude square waves into 1 megohm, which is what we need for scope cals. If you guys have any questions, as always, leave them in the comments below. I do check the comments regularly. If you have any suggestions, let me know. If there's anything you'd like to see, let me know. We'll see what we can try to make happen. I will see you guys in the next video.